All right. Hi, everyone. Sorry, I'm a little out of breath. I just made it in time. So I'm absolutely delighted to present to you all Ryan Sanders, who started very recently at the University of Kentucky, went over, and I saw a talk of his, and I thought it would be very interesting to hear his approach to chemical abundances. I'm trying to remember what your CV is, but I know that you spent some time on the West Coast and you are a spectroscopist. So,
True.
uh,
Yeah.
with the UV focus and the habitable worlds being primarily also a spectroscopy this stream, I'm really hoping to hear what you have to say regarding galaxy populations and spectroscopy. So, without further ado, and before I run out of more breath, Ryan Sanders, take it away.
Yeah. Thank you. Thank you, Bede, and thank you, Aaron, for inviting me to this. I should also say thank you for rescheduling my talk after we had scheduled this some months earlier. It became apparent that my talk was on the JWST cycle for proposal deadline day. Um, and as someone who uses a lot of JWST, that was definitely suboptimal for me and maybe for many of you. So fortunately, Aaron and Bene were very generous and scheduling me for a later open date so that I could spend my time frantically revising and submitting proposals instead of giving this talk on that Wednesday. So thank you very much for the flexibility there. Yeah, so I'm going to talk today about ways that we're understanding galaxy formation and galaxy mass growth through the lens of measuring chemical abundances of galaxies. And so as far as connections to HWO, I only have like one slide that's explicitly connecting to HWO, but the real thing is that HWO has the potential to provide a lot of access to chemical abundance measurements through unique combinations of UV and optical that are difficult to get right now because we have to go to the space for UV and we do optical from the ground. But at high redshifts, and I'll show this later with JWST, we can actually simultaneously access with JWST near spec, for example, the rest UV, the rest optical, and the rest near infrared with a single instrument, a single spectrograph on a single telescope. That's really, really powerful. And so if we had an analog at low redshift, a more powerful UV spectrograph than, for example, COS on HST, it would really open up a lot of ability to provide local context to things that we're seeing and mysteries that we have at the very high redshift universe. Okay, so galaxy formation, basically trying to answer the question, how does the baryonic content, the baryonic mass of galaxies grow over time? And often we use the stellar mass as a tracer of how the baryonic mass of galaxies is building up. Why has this been a difficult problem? Well, we very much well understand how the dark matter mass component and dark matter structure in the universe assembles over time. Lambda CDM really excellently describes the growth of dark matter structure in the universe, and that's because it interacts in simple ways, namely only through gravity, and it's not self-interacting, at least in the Lambda CDM paradigm. In context, baryons are extremely self-interacting. They can interact in very, very many different ways. And so as opposed to dark matter structure, which sort of monotonically collapses in an organized sense, on the right, you see a numerical simulation from illustrious TNG of a galaxy forming, and this is showing the gas density essentially in this formation simulation. As you can see, it's not really a simple monotonic process. There's gas moving in, there's stars being formed in the ISM, but then there's also gas being blown out by feedback in energetic processes. Gas that's moving out is interacting with gas that's accreting in, and that's changing things. And so you can see it's a messy process. It's difficult to parse out the details. So we like to take that messy process and, put in a really cartoon, simple picture of galaxy growth. And for secular growth, that is, growth of stars formed within the galaxy in situ, this is described through what we call the cycle of baryons. So we have some really basic physical mechanisms and parameters associated with this that can describe the growth of galaxies through this baryon cycle. We have gas accretion described by the mass inflow rate. Once gas gets into the ISM, it can cool and form stars. So the star formation rate in the interstellar medium is of interest there. But then once we're forming stars, or once we have gas in the center of galaxies, stars will die as supernovae, or gas will accrete onto supermassive black holes. And that will inject energy back into the ISM gas and heat it. It can blow gas out of the galaxy and outflows. It can heat the gas, which can slow down and regulate the star formation rate. Gas outflows can be very powerful, especially in early high-redshift galaxies. Then we get higher order things like gas recycling of past outflows that might be reaccreted onto the galaxy. So this is a cartoon picture, but it turns out it's been really difficult to get quantitative constraints on some of the parameters of this simple model, in particular things like mass inflow rates or mass outflow rates of galaxies. These are difficult to parse. We can measure things like stellar masses and star formation rates of galaxies, but to really understand the formation process and to try to parse out more details of formation histories, we need to understand what's going on with the gas flows as well. Okay, so how do we use chemical abundances to understand this problem? Well, here's a periodic table of the elements, right? We have many different chemical elements that are produced naturally that we might use to trace the evolution of galaxies. But astronomers, for the most part, we tend to slightly simplify this situation, right, into metals. So things basically produced by stars or the lives or deaths of stars versus things that are produced by Big Bang nucleosynthesis, namely hydrogen and helium. And so we simplify this process to having, things made by stars and then things that have been around since the Big Bang. And in particular, for studies of the metallicity in the gas phase rather than in the stellar phase, we often use one element, oxygen, as a tracer of the bulk metallicity. Now, there's some reasons why this is a good idea. For one thing, oxygen is the most abundant element in the universe after hydrogen and helium. Roughly half of all metals in the universe are oxygen, and so it's a good bulk tracer of the majority of metals. The other thing that's nice about oxygen is it's almost entirely produced by massive stars that will die as core collapse supernovae, and so these stars have very short lifetimes. So after we have a star formation event, you can essentially model the production of oxygen as an instantaneous enrichment after you form a new generation of stars. This greatly simplifies the modeling process. We can use what's called the instantaneous recycling approximation instead of having to track the time evolution of an aging stellar population for enrichment of stars of different masses that have different lifetimes. So that simplifies our modeling. If we trace oxygen, it's essentially instantaneously produced when we make a new stellar generation. And so the symbol we use for this is 12 plus log over h because we archaically add 12 for some reason that's buried back in history. Okay, so a really simple way to understand how metals can trace the buildup of mass in galaxies is because metals are produced in stars. So the more stars you form, the more metals you form. The more supernovae go off, the more oxygen comes out. And so to first order, the mass of metals produced by a galaxy is proportional to the integral of the star formation rate over time. And the integral of the star formation rate over time is essentially the stellar mass of the galaxy. So in a really basic sense, we expect that the metallicity of the galaxy increases over time as gas is converted into stars. But this is a really simple situation defined by this really simple equation that we refer to as a closed box model. There's no gas inflows or gas outflows in such a simple predictive model that would just say metallicity monotonically increases over time. And so if we go back to the cycle of baryons, we can essentially view each of these physical mechanisms in the cycle as either a source term or a sink term for metals that would lead to either a net decrease or net increase in the metallicity if you were to increase or decrease the rate associated with that mechanism. So accreting gas tends to be unenriched if it's being accreted from the IGM. It hasn't been significantly enriched by galaxies yet, by stars. And so that will lower the ISM metallicity by diluting the metals. Star formation, of course, can increase the metallicity because you're converting hydrogen into more metals. That's going to raise the metallicity. Feedback and outflows tend to be a negative term for the metallicity. So for one thing, outflows can eject newly formed metals from the galaxy completely so that they don't end up mixed into the ISM. But you can also get the effect that feedback, as I mentioned earlier, heats the ISM. It will regulate and slow down the star formation, leading to a lower star formation rate than you would have in a feedback-free model. And so that slows down the metal production rate. And then finally, recycling or reaccretion, can slightly modulate things because a past outflow is actually going to be enriched in metals. And so if you reaccrete that gas that was blown out earlier, it has some pre-enrichment compared to pristine gas accretion from the intergalactic medium. So that's how we can view this. Very quickly, just on how we measure gas phase chemical abundances. So most often we do this from rest frame optical spectroscopy for oxygen abundances. So here's a sort of typical spectrum of a star-forming galaxy. The bright, or what we call strong lines, are labeled here of oxygen, hydrogen, nitrogen, sulfur. If we want to use the gold standard way to measure chemical abundances, we use what's called the direct method. This is a method that's based on constraining the electron temperature of the ionized plasma in H2 regions. You can do this by measuring two lines of a single ion that come from different upper energy levels for the electron transition. So for example, we could compare what's called the auroral O3 4363 line to the strong O3 5007 line. So the upper energy level of 4363 is level 5, and the 5007 line comes from level 4. So because those have different upper energy levels, they have different excitation energies to populate those levels. And so it traces the electron energy distribution, and we assume these are in thermal equilibrium. So it's a Maxwell-Boltzmann energy distribution of the electron energies that can be described by the mean temperature of that Maxwell-Boltzmann distribution. And so that's how we get the electron temperature from emission line measurements. And then if you have the temperature and also the electron density of the gas, you can calculate the theoretical emissivities of each emission line transition. That's basically just an atomic physics calculation based on things like radiative transition probabilities, collision strengths, et cetera, from the atomic data that's either theoretically calculated or measured in the lab for different ions. So then you compare the observed line ratio of, say, an oxygen line to a hydrogen line to the emissivity ratio from theory of those two, and that directly tells you the ratio of the number density of those two ions. So in this case, doubly ionized oxygen to hydrogen for this example. So this is the direct method. It's the gold standard way to get chemical abundances, but it has some drawbacks. And one of the significant ones is just that these auroral lines are very faint, and so they're very difficult to measure. Most galaxies and large spectroscopic campaigns will not have detections of this auroral line. As an example, the Sloan Digital Sky Survey spectroscopic sample of the low redshift universe, there's hundreds of thousands of galaxies with detections of these strong, bright optical emission lines. But there's only of order less than 1,000 that have detections of the O3 4363 line. So you can see it's only a subset. It's also a very biased subset because it's only some of the brightest line emitters that have that detected in SDSS. So if we don't detect these faint auroral lines, we only detect the bright lines, we rely on something called a strong line calibration. And so this is where we start with a small sample that has this temperature-based direct method metallicity. We find correlations between the direct metallicity and strong line ratios of the bright lines, and then we fit lines through them, and then we use those calibrations to infer the metallicities of samples for which we only have bright line detections. So this is the most common way to measure metallicities in large samples of galaxies. So this has taught us a lot, though. So with strong line methods, for example, in the seminal paper from Krishi Tremonti back in 2004, this is the relationship between metallicity and stellar mass from the Sloan Digital Sky Survey, about 100,000 galaxies, again using strong line methods. And we can see that there's this nice tight relationship between mass and metallicity we see in the local universe. And the great thing is that the shape and normalization of this mass metallicity relation is highly sensitive to the properties of feedback and outflows. So if you do things like change whether outflows are energy versus momentum driven. If you change the mass outflow rate or the way it scales with stellar mass, you get very different predictions, for example, for models or simulations, for the shape and the slope of the mass metallicity relation. And so what we've learned at redshift 0 from this is that outflows are increasingly more efficient at removing material in lower stellar mass galaxies. And this has been directly constrained through direct observations of outflowing gas in a small number of galaxies at redshift 0. This is some work from John Chisholm. Okay, so that's all some stuff we've learned at redshift 0. We'd like to look at this same problem at higher redshifts. At earlier times, we know that galaxies have higher star formation rates at fixed stellar mass. Gas fractions are higher at fixed stellar mass. And we think that accretion rates should also be higher at fixed stellar mass. And so all of this tells us that the baryon cycle is sort of more intense, more extreme in high redshift galaxies than in low redshift galaxies. And so we'd like to understand the baryon cycle at high redshift. We'd like to understand how galaxy formation proceeds in the early universe and whether that differs from the way things are happening in the local universe. So to do this, we have to move to different spectroscopic instruments. One thing is if you move to high redshift, say redshift 2 to 3, that we often call cosmic noon, the rest frame optical emission lines will have been redshifted into the near infrared. And so one way we did this was by carrying out the Mossfire Deep Evolution Field Survey with the Keck telescope, the Mossfire spectrograph on Keck 1. To get rest frame optical measurements of the strong optical emission lines for galaxies at roughly a redshift of 2. And with these, we could then use strong line calibrations to infer the metallicities. Now, one question is, could we actually just detect these auroral emission lines for high redshift galaxies so that we could, have robust strong line calibrations to work in the high redshift universe? There's some reasons that we believe that these metallicity calibrations will not be exactly the same at high redshift as they are at redshift 0. But at the current time, these calibrations are, have only historically been constructed with redshift 0 galaxies where you have the measurements. So it's super duper hard, but it turns out with a lot of deep measurements, we can scrape by some sort of sometimes marginal detections of these auroral lines in high redshift galaxies. So here's an example of several oxygen 3 auroral lines over here, oxygen 2 auroral lines over here for galaxies at generally redshift 2 or so. And this is many dozens of hours on 10-meter class telescopes to get this information, but we're still mostly getting sort of like 3, 4, 5 sigma detections. So it's not, the most precise science, but it's the best that we can do. So with about, 15 years of observing campaigns trying to get these auroral lines, we really only came up with a sample of about 20 high redshift galaxies that had detections of these in the pre-JWST era. And we compared them to local calibration. So for example, this black line is what's defined by local H2 regions in these spaces. And the blue are the high redshift, and the orange is the median of the high redshift points, because we don't have enough statistics to actually trace out the shape of these things with this sample. But we found that the average of the high redshift sample agrees with calibrations based on what we call local analogs. So these are some of the most extreme galaxies in the local universe. For example, they have very high specific star formation rates similar to what's observed at redshift 2, for which we can actually do these calibrations. And by analogy, we can extend the calibrations for local extreme galaxies to say, hey, we think these would work at redshift 2. This seems to hold up based on a small sample of actual in situ high redshift measurements. So we took those analog calibrations, we applied them to a sample of several hundred galaxies from the MOSDEF survey that only had strong line measurements, and we inferred the metallicities for these galaxies so that we could look at the evolution of the mass metallicity relation from redshift 0 out to about redshift 3.5. So that covers about the past 12 gig years of cosmic history. This was really a step forward, but before Mossfire essentially was put on Keck, the sample sizes for this type of work were typically only about 30 or 40 galaxies with individual detections of these lines. People had to rely on stacked spectra, et cetera. So we really moved into a regime where instead of being statistic limited, we're now systematic limited, where we have hundreds of galaxies. So the statistics are very good, but we need to worry about systematics. Like, are we using metallicity calibrations that will yield the correct result for these high redshift galaxies that are more extreme than what we see in the local universe. So that's a big concern moving forward. But what we saw here, one very striking thing is that if we compare redshift 0 to 2 and 3, it seems like the low mass slope of the mass metallicity relation doesn't really evolve with redshift. Of course, we see a steady evolution towards lower metallicity at fixed mass as you go to the earlier universe. But it seems like the slope of this relation does not evolve. And so generally, this sort of slow and steady evolution agrees with what we see in many different cosmological simulations. And this low mass slope being similar suggests that perhaps the same physical mechanism is setting this slope both in the low and high redshift universe. We know at redshift 0, this slope is set by how the efficiency of outflows scales with stellar mass, what we call the mass loading factor, the mass inflow rate divided by the star formation rate. And so maybe that's the same at high redshift. So we applied some analytic chemical evolution models from these gas regulator family of models to infer the mass outflow, the mass outflow loading factor, mass outflow rate divided by star formation rate. And we indeed see that the scaling with stellar mass is essentially the same over this wide redshift range, eta out proportional to stellar mass to roughly the 1/3 power. This is quite interesting because this is also very similar to the theoretical expectation for momentum-driven winds for these supernova-driven outflows. So these are the results that we were getting in the pre-JWST era. But I want to spend the rest of the time talking about where we've been going from here now that we have the capabilities of JWST to get more sensitive measurements in the high redshift universe and also extend to higher redshifts than we could before. So one other thing I'll quickly mention, I mentioned earlier how we expect that some of these metallicity calibrations probably evolve as a function of redshift. So they're not the same at redshift 0 and high redshift. Why do we think that? Well, one of the big things is that if the sort of ionization state of the ISM changes as a function of redshift, so if the physical properties describing the ionized gas change with redshift, things like the hardness of the ionizing spectrum that's ionizing the gas, the ionization parameter, or the electron density, if these change a lot as a function of redshift, it's going to result in shifts in the relationship between strong line ratios and metallicity. One piece of evidence we have is that in this line ratio versus line ratio diagram, this is the BPT diagram, redshift 2 galaxies are known to be offset from the sequence described by redshift 0 star-forming galaxies. And one way to understand this offset is that some of these ISM ionization conditions evolve with redshift and lead to a displacement in this parameter space. And so we can look at theoretical models, for example, photoionization models, to try to understand what properties might be causing this. This is work from Chuck Seidel in 2014, showing that if you harden the ionizing spectrum, so basically the green to pink sequence is going from a softer to a harder ionizing spectrum. You shift galaxies up and to the right in this diagram, which would explain the shift that we see. And what we eventually settled on for this problem was by looking at certain methods, we could basically try to constrain both the iron abundance and the oxygen abundance in these galaxies. So the oxygen abundance, we get constraints from the rest frame optical lines, like I've talked about. For the iron abundance, we've used some different techniques. So one has been fitting the rest frame UV continuum spectra of these galaxies, where the shape of that UV continuum has little bumps and wiggles that are sensitive to the iron abundance in the massive stars. And so that's one way we can try to get at the iron abundance. Another way we can do this is for the small number of galaxies that do have direct method metallicities. We can do photoionization models where we fix the gas phase metallicity to match the oxygen abundance measured from the direct method. And then we can uniquely fit for both the ionization parameter and the stellar iron abundance at the same time. A real key here is that the ionizing spectrum that emerges from massive stars is essentially a function of the iron abundance, because the more iron peak elements you have in the atmospheres of these stars, the more metal line blanketing absorption you have that cuts down the amount of UV photons. So essentially, if you have a very iron poor star, There's much less opacity in its atmosphere. You basically see in farther to the star before you reach the photosphere, where the optical depth is roughly 1, and that's in a hotter layer of the star that's deeper. And so the stars have a hotter effective temperature when you go to lower iron abundances. And so we can understand this as a function, as being a result of the young age of high redshift galaxies. So oxygen comes almost entirely from core collapse supernovae. I mentioned earlier how this is essentially an instantaneous enrichment on sort of 10 million year timescales. In contrast, excuse me, iron comes predominantly from type 1a supernovae, so white dwarfs that cross the Chandrasekhar limit. And that enrichment happens on much longer timescales, sort of hundreds of millions of years up to billions of years. And so if you have young galaxies that have formed the majority of their stellar mass in the past, say, few hundred million years or something like that, they are not going to have a lot of type 1a enrichment. And so they will be oxygen rich and metal poor compared to, for example, the solar abundance pattern. So with these methods I just talked about before, UV spectroscopy and photonization model fitting, we've inferred that at redshift 2, the oxygen to iron ratio is on average something like 3 to 4 times the solar oxygen to iron ratio. And we think it's because these galaxies are forming very rapidly at early times. And as I said, this has implications for the ionizing conditions in the gas, because metal iron poor stars produce harder UV ionizing spectra. Okay. So now let's move forward to the JWST revolution. It's obviously been a huge thing for many different areas of astronomy, including galaxy evolution. Of course, you know, bigger mirror helps. We can either study fainter galaxies, or we can look at the same galaxies and just be able to detect much fainter emission lines, which is one of the keys here. But of course, also important is the increased wavelength coverage. Right. So with JWST, we have access, for example, with the NIRSpec instrument, to continuous spectroscopy across the 1 to 5 micron regime. So this is much better than Hubble. But another key is it's much better than we used to be able to do from the ground. So even with those Keck Mossfire near-infrared spectra, you can only get small chunks of wavelength that are in these windows where the atmosphere has a high transmission of infrared light. And any emission lines that fall in between those emission windows are essentially impossible for you to detect. In addition to this, you have the fact that the night sky is emitting much more brightly than the actual galaxies you want to observe in the near infrared. And so that makes it very difficult. There's a lot of foreground contamination that adds noise when you try to do the sky subtraction in the near infrared. So JWST has continuous wavelength coverage, and it's also not below the atmosphere, so we don't have to worry about any of these issues with atmospheric transition or with the night sky emission. So it's perfect for this. And so with the very first spectroscopic data that was released from JWST, we immediately saw the great potential for this to be a game changer for chemical evolution studies of early galaxies. So this is from the early release observations from the SMACS JO723 lensing cluster. And so this is a lens galaxy at redshift 7.7. So this is only 700 million years after the Big Bang. And what do we see in the spectrum? Oh my gosh, like an amazing auroral oxygen 3 4363 detection that enables a direct electron temperature-based metallicity for this galaxy. This is a redshift 7.7. You know, it's amazing. Again, from the ground, we were like struggling to do this at redshift 2 and 3. And so it just highlights the great gain in sensitivity and capability that NIRSpec has given us. So I love to do a side-by-side comparison. So we have many galaxies where we had the Mossfire spectra, and we've now observed them with JWST. So we can do a one-to-one comparison. So this is the Keck Mossfire spectrum. This is about 6 hours of total integration, 2 hours per filter, of a roughly 10 to the 9 solar mass star-forming galaxy, redshift 2.3. You can see some of these bright spikes, like this is the oxygen 3 line. This bright spike on the right is the H alpha line. Oxygen 2 is kind of buried somewhere down here. But then you can see the noise level is quite high, and we have a lot of spiky things from residuals from the sky subtraction. So it's very difficult to see if there's any faint emission lines present. And here's the exact same galaxy measured with JWST NIRSpec for 50 minutes per grading from space, right? And it's night and day. These are on the same scale, but you can see stuff that would have been completely lost in the noise from the ground. We can now see that JWST can detect many, many faint emission lines that we never would have been able to get. In addition, you see the huge increase in wavelength coverage that you get with JWST, except for a few small gaps that are in between the two detector chips on near spec where you can lose a small amount of coverage. So this just means we have an amazingly increased diagnostic power for the chemical and ionization state of the ISM in these galaxies with near spec versus what we could do from the ground pre-JWST. So for example, this is a redshift 4.5 galaxy observed from the Sears early release science program. And I've highlighted many of the lines here. This one down here is the auroral oxygen 3 line for electron temperature measurements. But we can also detect lines from many different elemental species now. So instead of just sticking with oxygen as our tracer of the metals, we can try to be more multidimensional and observe the multi-element abundance patterns of these galaxies and try to get more detailed constraints on their formation histories and their formation timescales. Okay, so what have we done over the first couple of years with JWST? So one thing that I've highlighted is the importance of understanding what's going on with these metallicity calibrations as a function of redshift. I know, so, talking about calibrating things can make eyes glaze over a lot, but there's really a lot of important results about metallicity evolution. And if we're not using robust metallicity calibrations, all of those results are biased, so I do think it is important to invest in this. So just from the early data from the first several months with JWST, I presented here some results from 2 papers, one of mine, one from Isaac Lassiter from JADES. We have something like 30 or more new auroral line detections for electron temperature metallicities at high redshift just in the first 6 months or so of JWST. And so we compare this to, 15 years of painstaking work from the ground. And just with a few months of JWST, we've already exceeded that significantly, right? So we wanted to do even better than these early programs. One program I'll highlight here is called the Aurora Survey. This is co-led by myself and Alice Shapley at UCLA and an excellent team that I've listed here on the right. This is a Cycle 1 JWST program that took very deep spectra of about 100 galaxies in 2 pointings, one in the Goods North field and one in the Cosmos field if you're an extragalactic aficionado. But the idea is that we were going to stare at, relatively bright redshift 2 and 3 galaxies. So ones that are similar to what we looked at from the ground in MOSTEP, for example. But we're going to go super deep with JWST. So we have 24-hour on-source integrations for these galaxies, spanning the full 1 to 5 micron range with continuous coverage with moderate spectral resolution so that we can resolve most of the important lines that we see here. And so one of the main science cases of this program was to detect these auroral lines to recalibrate the strong line relations to be robust in the high redshift universe. So this is just a redshift histogram of the targets of Aurora. You can see we have some galaxies at very high redshift, but we really focused on galaxies at the sort of cosmic noon redshift 1.5 to 4 or so as the main sample where we can really get detailed measurements compared to fainter galaxies in reionization or something like that. So, it's really great when things work out. I always like to look back. This is a figure from our Cycle 1 proposal that was a simulated spectrum from the exposure time calculator. And you know how it is with the proposals, right? You usually put something in that's a little bit of a optimistic, prediction for what you're going to get with the proposal, and this is an example we put in here of a simulated spectrum based on measurements of the strong lines from Keck Mossfire. But near spec is so good that it's essentially equaled or exceeded the detail that we expected to see in these spectra. So here's just a gallery of several aurora spectra of galaxies from redshift 2 up to about redshift 7. We see some different types of galaxies. We have a couple quiescent galaxies, a couple AGN, but mostly star-forming galaxies. And we can see dozens and dozens of detected emission line features in these spectra, including the faint auroral features for electron temperature measurements. So here's just another highlight. This is a redshift, I didn't put it on here. I think this galaxy is at redshift 1.8 or 1.9. And we can see that there are, several dozen emission lines detected, including like this is the oxygen 2 auroral line. There's an oxygen 3 auroral line over here. We've got lots of hydrogen recombination lines to constrain things like dust reddening. So just a humongous amount of detail, rich data set. And so what do we get with this? We've basically got about 50 galaxies with at least one auroral line detection. And we've got something like a couple dozen galaxies that have 2 or more auroral lines detected, which can help us understand the temperature structure across different ionization zones in these nebula. The other thing that's important here is we're no longer, like having an average signal to noise of like 3, where we're barely scraping by with these detections. We're really starting to detect things at high significance so that we can beat down the error bars on these measurements. So what are we doing with this? So this is kind of a little plot of like the evolution of strong line metallicity calibrations at high redshift. So circa 2020, we had the ground-based only sample that I showed earlier. So this was something like 20 galaxies or so. We can see these points. It would be pretty brave to say that this is enough data to, draw functions through this and say you calibrated anything. So we certainly didn't do that back then. Then fast forward to early 2024, we have the results both from my earlier paper with Sears data, as well as Isaac Lassiter's from the JADES program. And we've significantly increased the sample here compared to the ground-based sample. And we can start to see that we're tracing out shapes in these calibration spaces. We can see that like O32, neon 3 to O2 are anti-correlated with metallicity, similar to what we see at lower redshifts. We can start to see this turnover in O3 and R23. So we're really starting to trace this out. One thing that we're really lacking here, though, is galaxies at higher metallicities. So, we see that the majority of the sample cuts off around 20 or 30% solar metallicity, and we really don't have things in the relatively moderate and high metallicity regime. And that's because auroral lines are easier to detect at lower metallicity because the gas is hotter, and if the gas is hotter, then the auroral lines are stronger. So that's where Aurora comes in. Because of the deep spectra of these, bright cosmic new galaxies, we can really start to fill in the high metallicity end of these plots, and we can more clearly see the shape of these relations in these strong line ratio versus metallicity plots. So this is really going to allow us to basically revise our efforts to measure oxygen abundances from the strong lines moving forward. And we could even start to do things like slice and dice the sample as a function of redshift or other properties to see if there's systematic shifts of the calibrations if you have different sample properties among the high redshift galaxies. So at this point, we've reached a point where we have more than 100 high redshift galaxies with robust auroral line measurements compared to the less than 20 that we had in the ground-based era. So it's really letting us move forward. We'll be able to revise all of those earlier results on mass metallicity evolution with more accuracy. One thing I'll mention is that, if we compare these new calibrations to these local analog calibrations, these extreme redshift 0 galaxies I mentioned earlier, the agreement is actually not so terrible. So we don't think that those earlier results based on the local analogs were completely off base, but we'll, of course, be able to do a better job when we calibrate these things in situ at high redshift. Okay. So that was about the oxygen abundance, but like I said, we can actually trace the abundance of several different element species with these very detailed JWST spectra. So going back to this periodic table, this was produced by Chiaki Kobayashi, and things are color-coded by their relative fractional origin from different enrichment sources. So high mass stars are things that die as core collapse supernovae on short time scales. Intermediate mass stars are things that enrich as asymptotic giant branch stars on sort of 100 million year timescales. And then the red things are stuff that comes from type 1a supernovae on longer timescales, gigayear and longer. And then, of course, we have some elements from neutron star mergers that LIGO has taught us things about more recently. But the cool thing here is that if you can measure the abundance ratio of an element that's produced on short time scales like oxygen versus an element on long time scales like iron or on intermediate time scales like carbon or nitrogen, you can compare those ratios to predictions from chemical evolution models to basically constrain the formation timescales and the formation histories of these galaxies. So these abundance ratios can be used as sort of cosmic clocks to constrain the timescale of galaxy formation in different samples when you can measure multi-element abundance patterns. So how does this work? This is just a really simple chemical evolution model where we basically have a single burst of star formation at time 0, and then star formation cuts off, and we just see how the element abundances proceed as you have enrichment on different timescales. So first, on sort of 10 million year timescales, we have the enrichment from core collapse supernovae. This produces a lot of oxygen and neon. Of course, it produces some of these other elements, but relatively low amounts. So things like C over O, N over O are going to be low just after core collapse supernova enrichment. When you go to more intermediate time scale, so around 50 to 100 million years, we have the high mass AGB stars, which enrich the galaxy in nitrogen. You can see this big jump up in nitrogen around several tens of millions of years. We go out to about 100 million years or so, we get enrichment in carbon from the lower mass AGB stars, where you see in the blue line, the C over O ratio jumps up. And then at late times, and actually over a very wide time distribution, you get the type 1a enrichment. So this brown line is iron. We can see that iron to oxygen is very low for core collapse supernovae only enrichment. But as type 1a start to go off, you get this steady rise over very long timescales to much higher iron relative to oxygen. And so I mentioned that earlier with the work we did from the ground. Okay, so if we can measure these abundance patterns, like I said, we can try to do things like identify, some of the youngest stellar populations in the early universe. And so we did this with some early data from the GLASS early release science program. So this is a paper led by Tucker Jones that I was involved in. So we used REST UV measurements of carbon-3 and oxygen-3 from JWST to constrain the C to O abundance ratio in a galaxy at redshift 6.2, so about 1 billion years after the Big Bang. The result is the red star here. We find that it has a very low C over O, about -1 in log, which is as low as the lower envelope of anything that's been observed in lower redshift samples. And it's very close to what you would expect from sort of pure core collapse supernova enrichment, which would mean that the galaxy has formed most of its stars within the past less than 50 million years or so. And so this was just a sort of proof of concept with early data that we could make some of these measurements. Okay, so with these very deep spectra with Aurora, we're trying to do even better than that, get better constraints on the temperatures, better direct method abundances, and also move on to more elements than just, say, C over O. So I'll highlight one galaxy to wrap things up. This is Goods North 17940. This is at a redshift of 4.4. It turns out we actually had a spectrum of this with Keck Mossfire, where because of the high redshift, we could only detect the bluest optical lines. So we had marginal detections of oxygen 2, neon 3, and H gamma. You can see in the spectrum down here. The red line is the error spectrum. So you can see that the signal in black is only, these are not super high signal to noise detections. But we took this measurement back in 2017. We used the neon 3 to O2 ratio in combination with metallicity calibrations to estimate its metallicity and try to look at how the mass metallicity relation was evolving in normalization all the way up to redshift 4.4. Okay, nobody would say that this is a very, robust metallicity just from this very limited information. But it turns out this galaxy also made it on our Aurora masks with JWST, where we got very deep spectra. So this is the Mossfire spectrum, and in the same wavelength range, this is the JWST spectrum. And the error spectrum is the gray band at the bottom. So as you can see, the signal noise is extremely high. Instead of just marginal detections of a few lines, we have high signal detections of about a dozen lines, including a very strong detection of the oxygen 3 temperature-sensitive auroral line. We even have things like auroral sulfur 2 line down here that's detected. And this is only a tiny chunk of the wavelength, right? So with the wide coverage of JWST, this is the full spectrum. This spectrum is amazing. It has more than 70 emission and absorption line detected at a signal noise greater than 3. And so we're kind of, swimming in, borderline too much information to try to figure out what's going on with these galaxies now, which is a great place to be, an embarrassment of riches. So what can we do? Well, we detect, many different hydrogen recombination lines. This can allow us to make robust corrections for the dust reddening and dust attenuation in these galaxies. This is very important because many of the temperature-sensitive ratios with those auroral lines are widely separated in wavelength, and so you need to do a robust reddening correction to get robust temperatures. So it's very important for us to do this well. So we've used the measured H1 recombination lines all the way up from the Balmer 12 line down to Paschen series lines out in the rest frame near infrared to constrain the shape of the nebular attenuation curve in this galaxy. The result we get is this red curve, which actually strongly deviates from the curves we typically assume to hold at high redshift. So things like the Milky Way extinction curve or the Calzetti starburst curve measured in local galaxies. So this tells us that it might not always be a good idea at high redshift to just assume one of these common curves like the Milky Way for your dust correction. So with the full aurora sample, we're going to be able to constrain the galaxy to galaxy variation in the dust curve for a sample of a couple dozen galaxies. So it'll be very exciting to really understand how much that varies galaxy to galaxy. Another cool thing in the dust curve we find is that there's basically, there's no 2175 angstrom bump in the UV, which is something that you see in some dust curves like the Milky Way. We don't see it at all in this galaxy. I'll come back to that later. So electron temperature constraints. We detect 6 different auroral emission lines in this galaxy. Oxygen 2, actually 2 oxygen 2 auroral lines, one in the UV and one in the rest optical. As well as sulfur 2, sulfur 3, oxygen 3, nitrogen 2. I put on the bottom the ionization energies of these different species. And so the 35 EV should be over here with oxygen 3 and 13.6 should be over here with oxygen 2. Little mix up there. But you can see we're constraining electron temperature across a wide range from low to high ionization species, which is important because there can be variation in the temperature as a function of the ionization structure within the nebulae. And so this allows us to account for that when we do our abundance calculations. Okay, so we detect lines from many different ions. I've just highlighted some here: oxygen, sulfur, nitrogen, silicon, neon, argon, carbon. And so we can do an elemental abundance pattern with many elements here. We also detect lots of helium lines. We can measure the helium abundance. Thought this was, quite cool. This is 8 detected helium-1 emission lines. And this is a best fit model based on the theoretical helium-1 atomic data. And we can see it matches beautifully with the measurements that we get for this galaxy. And so we can get robust abundances of helium as well. And so the takeaway for this galaxy at redshift 4.4 is that we can measure an 11-element abundance pattern 1.5 billion years after the Big Bang. This is something we've never been able to get close to with pre-JWST data, or even with relatively shallow JWST data from early programs. So here this shows helium to hydrogen on the left, and then different metals relative to oxygen for all the ones going forward from there. And these are all put on a solar scale. So it's basically the log of whatever abundance ratio relative to the solar abundance ratio. So a solar abundance pattern would be at 0 across the board here. Okay, so what can we do with this? Well, going back to these sort of simple chemical evolution models, we can try to match a particular, age in these abundance models to understand to the abundance ratios we see to understand the formation timescale of this galaxy. So one thing that's important to take into account is the effects of dust depletion. So some of these elements that we measured will deplete onto dust grains. And so when dust depletion happens, these elements leave the gas phase, which is what we're measuring, and they condense onto dust grains. And so it would decrease the abundance of those elements that we measure in the gas phase, but it needs to be taken into account to understand the actual intrinsic abundance pattern of the galaxy as a whole. So one way we can do this is by comparing the relative ratios of different elements that deplete more and less heavily onto dust grains to constrain this. I know I'm running a little short on time, so I'm probably going to go a little fast through this. But if we look at this right plot, this shows lines from chemical evolution models where we start with pure core collapse supernovae enrichment. And then moving to the right, you have an increasing degree of type 1a enrichment. And so the x-axis is the mass in metals from type 1a supernovae divided by the total mass in metals that have been produced in the model. So basically, as you move to the right, you have a higher relative importance of type 1a enrichment relative to core collapse supernovae enrichment. This is similar to a galaxy that is older and older over time. If you want a scale here, roughly solar iron to oxygen is reached at about 0.15 on the x-axis. But on the right panel, what's important here is that this shows in brown the argon to sulfur ratio, assuming different core collapse supernova input metallicities, and then in pink, the silicon to sulfur ratio. And it turns out that both of these ratios, argon to sulfur and silicon to sulfur, these elements are produced both in core collapse and type 1a supernovae, but they're produced in essentially the same ratio in both. And so what I'm showing here is that these two abundance ratios show very little evolution, whether you're dominated by core collapse or dominated by type 1a. And so that means that regardless of if it's a young or old galaxy, we have a prediction for what the intrinsic argon to sulfur and silicon to sulfur ratio should be. And so what we find is that, silicon to sulfur and argon to sulfur are basically constant as a function of, the stellar population age in these enrichment models. We can use that to constrain the dust depletion. So there have been measurements from in the Milky Way, the LMC, the SMC, and also in damp Lyman alpha absorbers of the relative depletion patterns of different elements. So the y-axis here shows the depletion of different elements. This is basically gives you a handle on what fraction of the element has been depleted into dust. So this is basically the log of the depletion fraction. And on the x-axis, we have this parameterized as the zinc over iron abundance ratio. We don't actually need to measure it. What's just important here is that all elements show an increasing amount of, all elements that deplete onto dust grains show an increasing amount of depletion as this zinc over iron increases. And so we can use it as a parameterization of the total degree of depletion. So what we see here in silicon versus sulfur is that at fixed zinc over iron, you see a stronger depletion in silicon than you do in sulfur, for example. So it's been measured for many different elements. If we think of our argon and silicon versus sulfur, argon doesn't deplete at all since it's a noble gas, so it's not reactive. We have these intrinsic ratios. We can compare those to the ratios that were measured for Goods North 17940. So the brown line is the measured argon to sulfur ratio, and the silicon to sulfur ratio is in pink. And we can see that there's an offset relative to those intrinsic and relatively stable ratios that are shown in the thin lines. And so we can basically find the zinc over iron value that when you take into account corrections for depletion can convert these observed values to match the intrinsic theoretically expected values. Particularly, we get a fit of zinc over iron of about 0.36. And once you know zinc over iron, you can correct not one of these elements, but actually all of these elements for depletion based on the depletion factors at that zinc over iron value. And so we've done that. So here we have the abundance pattern in green as measured, and in red, corrected for dust depletion. We see that the silicon has come up since it depletes moderately heavily, but in particular, correcting for dust depletion in iron is very important because it depletes much more strongly than these other elements. So what have we learned here? We see we have subsolar, argon to oxygen, sulfur to oxygen, silicon to oxygen. This is actually indicative of a lack of significant type 1a enrichment because All of those elements have a secondary non-negligible origin from type 1As. You can also compare this with results from Noah Rogers' 2024 paper on a redshift 3 galaxy with argon and sulfur to oxygen measurements. So we expect this galaxy to be iron poor if it's not enriched in type 1As. The depletion corrected iron to oxygen is minus 0.65 in the log. So this means that this galaxy is 4.5 times alpha element enhanced, which is consistent with essentially very little type 1A enrichment or essentially pure core collapse supernovae enrichment. We find that it has a low carbon to oxygen value over here, significantly subsolar, which would indicate little asymptotic giant branch star enrichment on sort of 100 million year timescales. But a tricky thing here is that actually the nitrogen is not low. So nitrogen also traces AGB stars, but the nitrogen is very high. It's roughly the solar value, despite carbon oxygen being very subsolar. That seems at odds with each other, but we can actually explain this because we see both high nitrogen, but also a helium enhancement in this galaxy. And that's a key signature that the gas in the ionized gas in the ISM of this galaxy has been enriched by winds from Wolf-Rayet stars that can basically produce a lot of nitrogen, a lot of helium, and then blow that back out into the surrounding ionized gas as those Wolf-Rayet stars strip their outer layers down to the helium core. And so Wolf-Rayet stars are very, very short-lived, only a few million years. And so you would have to catch a galaxy in a very short time scale after a strong starburst to see this Wolf-Rayet self-pollution. And so that's what we think we're seeing here. We think this is a galaxy with a very young age that's very rapidly formed, and it's observed within a few million years of a massive starburst that's driving the strong emission lines. And the nitrogen and helium excess we see is due to self-pollution from Wolf-Rayet stars. I'll mention here that similar results have been proposed to explain the abundance pattern of GNZ11 at redshift 10.6 by Chiaki Kobayashi, and has also been seen in the Sunburst arc, which is a lensed redshift 2 galaxy by Rivera Thurston et al. And so this just shows how if we have more detailed constraints from deeper spectra, we can start to understand why we see abundance patterns, for example, in GNZ11 or these other redshift 6 to 7 galaxies here that deviate from the abundance patterns we see in local galaxies. It's not really until we get these detailed spectra with multiple elements we can truly understand the origin of these anomalous abundance patterns. Okay, so that's just a demonstration of the power of this deep JWST spectroscopy. Just to close the loop here, that was really enabled by having simultaneous deep UV and optical rest UV and rest optical spectra to trace elements. In particular, the UV is needed for carbon and silicon, and it also traces high ionization lines that are really useful for constraining the ionizing spectrum in these galaxies. And you need the optical for the temperature and density diagnostics for the direct abundance calculations. So if we want to do this now, we have to combine ground-based spectra with space-based HST spectra, and that carries loads of systematics. We can see here from the Galaxies survey, which has done this for about 50 local galaxies. One, these are all extreme galaxies that have very high star formation rates that are elevated roughly an order of magnitude above the redshift 0 main sequence. So we need more sensitive UV spectrographs to reach typical galaxies, not extreme galaxies. But additionally, we have to worry about aperture effects and biases between the HST COS aperture and the ground-based spectroscopic aperture. This is work from Classy from Carla Arellano Cordova. And so a future facility like HWO that could provide us with space-based UV and optical measurements would be an amazing move forward to basically provide a redshift 0 analog sample that's comparable to what we're going to have at high redshifts with years of JWST. JWST can give us the UV and optical for these very high redshift galaxies, but we really don't have a benchmark representative sample at redshift 0 that we can compare to in a one-to-one basis. And so HWO is one way that we can do that. So I'll wrap up there. Sorry for going slightly long, and happy to take questions from anybody.
I can never find the clap hand emoji, so I would just do a clap. Great. So at the top of the hour, but if there's any pressing question from the room, feel free to just unmute yourself and ask it away.
Hi, can you hear me?
Yes,
Yes.
loud and clear. Yep.
Yeah. Hi, this is Annalisa Citro from University of Minnesota. So I had a question about the chemical evolution models that you created to explain all the observations.
Yeah.
So you're not, are you like including also inflows and outflows in those models, or are they just closed box?
Yeah, so those models didn't include inflows and outflows. They're basically just a single starburst, and then you let the metal line ratio, the metal abundance ratios proceed from there. I will say that if you include outflows, the effect that you basically get is that so the outflows will happen on relatively short timescales after the core collapse supernovae. And so the outflows will preferentially remove core collapse enrichment products rather than long timescale enrichment products from AGB or type 1A. And so if you include outflows, it tends to basically result in quicker ramps up for iron and carbon and nitrogen, things with longer enrichment times. So the ones I had there were just for illustrative purposes, but one place we hope to go in the future is to actually use, fully detailed models to try to directly fit formation histories to the measured abundance patterns that we have.
Okay, thank you.
Thanks.
Hi, can I jump in with a similar question?
Sure.
Let's go ahead, Chris.
Yes. Also, hi Ryan, great. It was a fantastic talk. But following up on that question about adding feedback to
Yeah.
those one zone chemical models, you're talking about its effect on the ratios. But if those outflows are removing gas, which was already in the galaxy, then now those outflows would also be removing elements from those long duration timescales if that gas was already there from prior star formation events. So can you
Yes.
comment on how that could affect the ratio you would expect?
Yes, yeah. So the way that would affect depends on the star formation history. If it's a very long, drawn out star formation history, then that, relative increase in the importance of that relative increase in the long duration enrichment becomes less pronounced because if the star formation is very long and drawn out, then you basically get a smoother enrichment overall. But indeed, one has to just self-consistently track all of that in the way you implement these things. So if it's formed in a short burst, then the strongest outflows will happen when you essentially only have core collapse products in the ISM. The other thing that we've been putting into these models as a way to parameterize is you also need to include basically the fraction of the outflows that's in trained ISM, which is going to have one abundance pattern, versus pure core collapse ejecta, which will have a different abundance pattern.
Yeah, exactly.
So that's a knob we can also turn that changes the results of that. So trying to make those more realistic is work that's in progress. So I hope to have something more to show in the future, but I love these ideas. I think it's definitely where we need to go to make these more realistic, to model these galaxies.
Yeah, awesome.
Great. Well, let's wrap up here. Thank you for the nice seminar. All right. Oh, Benny?
I'll do it later. Ryan's so. All right.
Of course, if you have other further questions, you can always, for everyone, always reach out to Ryan. I think you can find his email online somewhere. So thank you all for joining us. We'll have another seminar in 2 weeks by Alison Strom. So see you all in 2 weeks. Take care. Bye-bye.
Thank you, everybody.
Thanks, everyone. Thanks, Ryan.